This video contains the solutions to take-home problems number 15. So here we have an application problem involving the height of an object that's been propelled vertically upward. So the height as a function of time is given by h of t equals this expression, and we see that it's a quadratic equation. And we want to know when will the object be 500 feet above the ground. So if h represents the height, then we replace the height by 500, and then this gives us an equation to solve. 500 equals negative 16t squared plus 240t. Subtract 500 from both sides, we get negative 16t squared plus 240t minus 500. Now, since the coefficient of t squared is not 1, we shouldn't really try to factor this, so we're just going to go ahead and use the quadratic formula. So our solution is going to be t equals negative b, so negative 240, plus or minus b squared, so 240 squared, minus 4 times a, which is negative 16, times c, which is negative 500. So there's lots of minus signs kicking around in this one, so we just got to be careful. And then divided by 2a, 2 times negative 16. And when we work all of that out, we're going to get two solutions, which is 2.5 and 12.5. And so that means that this object is 500 feet above the ground twice, after 2.5 seconds and 12.5 seconds. Now for part B, we want to know when will the object hit the ground. So we have to realize that if h represents height, then on the ground is where the height equals 0. And so, similar to what we did in part A, we're going to set height equal to 0. We get negative 16t squared plus 240t. And now this one we can factor, because we can just factor out a t. So we get t times negative 16t plus 240. That gives us two solutions. One of them is t equals 0, which makes sense because the object starts on the ground. And then the other one is going to be negative 16t plus 240 equals 0. So 16t equals 240, which gives us t equals 15. And so that's really the sort of more interesting time here, is that after 15 seconds, the object is going to hit the ground. But 0 seconds is a solution that makes sense as well, so because the object is on the ground at the beginning. Finally, if we want to think about the maximum height of the object, it helps to think about the graph of this function. If I were going to graph this height function, it's a parabola because I've got a t squared. The value of a is negative, and we know that it starts at 0. And so the height function is going to look a little bit something like that. So the maximum height is going to be achieved at this point here, which also happens to be the vertex of that parabola. And we know how to find the vertex of a quadratic function. The x-coordinate, or in this case the t-coordinate, is given by negative b over 2a. The b is the coefficient of t, so that's 240, divided by 2a, which is 2 times negative 16. And again, we work that out in our calculator, and we get 7.5 seconds. So that's when the object gets the maximum height. That doesn't tell us what the actual maximum height of the object is. For that, we need to plug into our function. So we need to figure out h of 7.5, which is negative 16 times 7.5 squared, plus 240 times 7.5. And again, when we work all that out, we end up with 900, and so in this case, the units would be 900 feet. Now this time we're given a demand equation for a product, and we're asked about revenue. So what we have to remember is that revenue is equal to price times quantity, in this case p times x. So if my demand equation was solved for one variable or the other, I could just plug that variable in. But unfortunately my equation is not solved for x or p. So I'm going to decide whether I want to solve it for p or whether I want to solve it for x. And thinking strategically here, if I solve for x, I'm going to have to divide by 0.03. That doesn't sound like it's going to be very nice. But if I divide by 2 to solve for p, that's not going to be so bad. So I'm going to do that. So I solve for p. I'm going to add 2p to both sides and subtract 0.03x from both sides. And then divide both sides by 2. So that's going to give me 25 minus 0.015x. So there's my price function. And so if I plug that in for p in my revenue function, I get r of x is 25 minus 0.015x times x, which is 25x minus 0.015x squared. Now we want to maximize the revenue, and so similarly to what we just did in the previous problem, we're looking for the vertex. So the vertex is where we get the maximum. Because the coefficient of x squared is negative, that means it's going to be an upside-down parabola, and the vertex is going to be where I have a maximum. So that's going to be where x equals negative b divided by 2a. That's going to be b is 25 in this problem, and a is 0.015. And that's going to work out to be 83.3 repeating. And that's the quantities. That's what x equals when revenue is maximized. But they're telling us to find the price that maximizes the revenue, which means we need to take that value of x and plug it back into our price function. So p is going to be 25 minus 0.015 times 833.33 repeating. And that ends up working out to be 12.5. But since this is a price, it makes sense to write this in terms of dollars and cents, so we'll write that as $12.50. So that's the answer to part A. Part B now says we want to know the actual maximum revenue. So there's a couple ways to do that. We could take our value of x and plug it back into our revenue function. But a little bit easier is that now that we have the price and the quantity, we can just multiply price times quantity. Remember, revenue is price times quantity. We can just multiply the price times the quantity to get the revenue. And so that's what I'm going to do, just because it's a little bit easier. So for part B, revenue is price times quantity. My price is 12.5. My quantity is 833.33 repeating. Again, on my calculator, that's going to work out to be 10,416.666 repeating. Again, this is revenue, which is dollars, so that's going to be rounded to 2 decimal places, $10,416.67. So there's my answer to part A, and there's my answer to part B. Finally, we have one of these, what we call uniform motion problems. So there's a lot of information here, but the basic idea is that we've got a round trip. We're traveling upstream against a current, and then we turn around and travel back downstream, and we want to know the speed of the boat relative to the water. So in other words, the speed of the boat if there was no current. So the way that I recommend doing this is to make a chart. You know me, I like my charts. So I'm going to have one row of my chart for the upstream trip. That's where I'm working against the current. And then another part of my chart for the downstream current, where I'm working with the current. And then since we're talking about motion, the three quantities we're interested in are distance, rate, and time, with the idea being that distance equals rate times time. That's going to be the relationship we're going to use. Okay, so now let's go back and read the problem and see if we can figure out what we're doing. Remember that what we're looking for is the speed of the boat relative to the water. I'm going to call that B for boat. So the B here represents the speed of the boat. So that's going to be the variable I'm going to use for that. So we're told that the point along the river is 20 miles upstream. So that means the distance in both directions is going to be 20 miles. Now for the rate, we know that the current flows at 5 miles per hour. The base speed of the boat is B. But when we go upstream, the current is working against us. So our speed is reduced by the speed of the current. So our regular speed of B, if it was calm water, gets reduced by 5 miles per hour. But when we turn the boat around to go back downstream, now the current is helping us, and so the boat gets speeded up by 5 miles per hour. All right, now they don't tell us anything about time here, other than the total time is 4 hours. So whatever my two times are, whatever I end up writing here, and whatever I end up writing here, if I add these two together, that should equal 4 total hours. So how do I figure out what to write in those boxes? Well, I know that distance equals rate times time. I haven't used that fact yet. So if distance equals rate times time, then time must equal distance divided by rate. So in the first row of my table, distance divided by rate looks like 20 divided by b minus 5. In the second row of my table, distance divided by rate looks like 20 divided by b plus 5. And I know that when I add those two times together, it should equal 4 hours. So now we've got an equation. 20 over b minus 5 plus 20 over b plus 5 equals 4. And as usual, once we get to the equation in a word problem, we're usually good to go, or at least better off than we were before we had an equation. It's the getting the equation that's the hard part. Okay, now what are we going to do? Well, we've got algebraic expressions in the bottoms of our fractions, so we're going to multiply both sides by b minus 5 times b plus 5 to get rid of those fractions. Now, whenever we do this, as we hopefully know by now, we've got to distribute. So we're going to get b minus 5 times b plus 5. times the fraction 20 over b minus 5 plus b minus 5 times b plus 5 times the fraction 20 over b plus 5, and that's going to equal 4 times b minus 5 times b plus 5. So on the left-hand side, b minus 5 and b minus 5 divide out, b plus 5 and b plus 5 divide out, and so I end up with 20 times the quantity b plus 5 plus 20 times the quantity b minus 5 equals, now over here, b minus 5 times b plus 5, multiply that out, we're going to get b squared minus 25. Multiplying out the left-hand side, we get 40b equals 4b squared minus 4 times 25 is 100. Now we've got a quadratic equation, and remember we want to usually move everything over to one side. So we get 4b squared minus 40b minus 100. And that's what we need to now solve. Now, in approaching this equation, we might think to immediately jump to the quadratic formula. We see that the coefficient of b squared is not 1, and so we might just use the quadratic formula. And there's nothing wrong with that. But you might also notice that we can factor out a 4. And if we factor out a 4, we end up with b squared minus 10b minus 25. And so when we see it like this, we think there might at least be a chance that this might factor. So we'd be looking for two numbers that multiply together to be 25, and the difference between those numbers would have to be 10. But think about that for a little while. There's not too many ways to multiply two whole numbers to get 25, and there's no way to get the difference between those two numbers to be negative 10. So it turns out that even though we thought there might be a chance this would factor, it turns out it doesn't factor. So we can just go straight to the quadratic formula. Now we factored out this 4, so we can use this simplified quadratic as the quadratic formula. If you want to use the original, you'll still get the same answer. Your numbers will just be multiplied by 4. So we get b equals, now we got to be careful here. We called our variable b, maybe that wasn't such a great choice. So when I think about the b in the quadratic formula, I'm thinking about this coefficient, negative 10. So plus or minus the square root of b squared, so negative 10 squared, minus 4ac, so that's 4 times 1 times negative 25. All divided by 2a, so that's 2 times 1. So we get 10 plus or minus. Negative 10 squared is 100, minus 4 times minus 25 is also 100, divided by 2. So we get 10 plus or minus the square root of 200, divided by 2. Now that gives us really two answers. So we've got 10 plus the square root of 200, divided by 2, and 10 minus the square root of 200, divided by 2. But when we go to our calculators, this second result, that's going to be negative. And we know that the speed of our boat can't be negative, and so we cross that one out. Plugging the other solution into our calculator, we get approximately 12.071, and that is going to be the speed of our boat in miles per hour.